All right, well, I think it's about time to begin. I apologize for last time um, where I didn't have the tech done very well at all. Hopefully, it'll work out okay today. I'm sorry for the webcam, which is just my laptop. But I wanted to just review some of the things we talked about last time because I know we went through it kind of quickly and I was all discombobulated. So our goal last time was to describe the wave function in a way that we could uh, figure out where the momentum and the kinetic energy operators came from. And so there have been some questions about, well, how much of this math do you need to memorize? And the answer is none of it. The reason I went through all of this last time is because when I was reading the text and the text talked about the operator for kinetic energy, I wondered where in the heck it came from. So this is my attempt to figure that out. So we went through the equation involving Planck's constant and frequency. We talked about mass energy equivalence. We talked about de Broglie's hypothesis or postulate that particles have wave-like properties and their momentum is related to their wavelength. And then we described a simple wave function, which, if you recall last time, was just a sine wave or a cosine wave. And we made some substitutions to finally come to the expression that the kinetic energy, to show you that the kinetic energy of a particle is related to, let's see, h bar squared divided by the mass of the particle, and then this del operator, which is the kinetic, which is the second derivative of the wave function with respect to space. Now, I want to pause there because, and if it's jumbled in your mind, that's okay because it's jumbled in mine. We're going to step back and get the big picture in just a second, but questions up to this point. Dakota, I am not ignoring your question from last lecture where you asked, what if the second derivative of your wave function, or what if you take this term, the kinetic energy operator, at any given point in the wave function, what if that term for kinetic energy is negative? And the answer to that question is kind of complicated, and I don't really understand it that well myself. But I wanted to just take a minute to try to tell you what I learned while I was gone. So the wave function is something you cannot observe directly. What we can observe directly are physical properties. And for example, if you wanted to know the average, say, radius of the hydrogen atom, the way you would do that, if you wanted to know, and we would call this, we would put the x in brackets, this is what we would call an expectation value for x. And suppose we wanted to know what is the average position of the electron, 1s orbital for hydrogen. So what we would do is we would take the wave function for the 1s orbital for hydrogen, and as a function of whatever space coordinates you want. Suppose we just want to, it's just in radius, so that's fine. And we would multiply that wave function by the position operator. Now, the position operator in quantum mechanics just happens to be r or x, whatever the variable that the position is. But we can't stop there because the wave function is a complex number. It has real and imaginary parts. So we have to pre-multiply the r times the wave function by the wave function with the asterisk. The wave function with the asterisk is the complex conjugate of the wave function. Complex conjugate, for example, if a function equals a plus b times the imaginary number, its complex conjugate is a minus b times the imaginary number. So that when you multiply complex conjugate by the function, you're going to get rid of the imaginary parts and come up with that. If I missed a sign there or did the algebra wrong, I'm sorry, but the imaginary parts either subtract out or are multiplied by themselves and go away. All right, and so what we would do is we would integrate this expression from r equals 0 to r equals infinity. And what this equation means is we want to know the probability, well, let's see. We want to know the probability of finding the electron in a small increment of space called dr at position r, averaged over all possible radii, and then you come up with an answer. Okay? And frankly, the math, I wish I could demonstrate to you that this number is always positive. I can't, because I looked up the wave function for the 1s orbital of hydrogen, and it's not that complicated, but it was too complicated for me to integrate without computational help. Nobody does this by hand anymore. So I'll ask you to accept on faith that, for example, this number is positive. The same thing is true for the kinetic energy. If we wanted to know the average kinetic energy of an electron in a 1s orbital for hydrogen, what we would need to do is take the complex conjugate of the wave function times the kinetic energy operator, which is opposite of h bar squared over 2m times the second derivative of the wave function integrated over all space. Okay? And again, you might ask, what's that negative sign for? And the answer is, I'm not sure, but it all works out such that kinetic energy is a positive number. Go ahead.
So it might be that multiplying by the complex conjugate might yield a negative somewhere?
Yeah, it could be that multiplying by the complex conjugate would yield a negative, or alternatively, it could be that the differentiation itself requires that. So if you wanted to go back to our wave function as we defined it last time, shoot, I forget, it was I over h bar times px minus energy t. If you take the first derivative of that with respect to x, you get I times h times p times just the wave function again. And then if you take the second derivative of that, you get minus p squared over h bar squared times the wave function. So if you were to, if this were our wave function and we put it in there, the minus sign that we get here would be canceled out by there, so we'd have a positive number. Unfortunately, that's the level at which I understand it. So I wish I knew more, but that's where we're going to have to be. We will talk soon about computational programs to do some of this math for us. You can actually do some of it in Mathematica. If you want to write your own, you could. I don't recommend it. I tried and failed. There are preset Mathematica files that allow you to play around with hydrogen atomic orbitals. But we're going to use later on in the semester a program called Gaussian to do some high-level molecular orbital calculations. Okay, so with that in mind, that brings us back Any questions on that? Brings us back to this qualitative observation that we made last time. Go ahead.
If the expectation value of radius were ever negative, it would be hard to visualize.
That's right. If expectation value, yeah, if it simply couldn't. And I guess one more thing on that sign of kinetic energy. Your question, I think, Dakota, specifically was, well, what if the second derivative is negative here or wherever? And the answer is, doesn't matter. Kinetic energy at a single point, you can't evaluate, because if you know that the electron is at that point, you no longer know anything about its momentum, so you can't know kinetic energy. So evaluating kinetic energy only has meaning over all space. So, and your text glosses over this entirely, which is why you caught me flat-footed last time. I've done the best I can. Nobody on the internet talks about it, so it's a really good question, but I'm afraid I don't have a good answer. We're going to think about evaluating how energetic a wave function is just by thinking about the magnitude of the second derivative. Don't worry about the sign, okay? So we talked last time about how the second derivative is the rate of change in the slope. So wave functions that are more spread out have slower changes in slope and therefore should have lower kinetic energy. That is a key finding, and it is general. This has some other consequences. And so this is the fundamental reason why we say, and why you learned in sophomore organic, that electron delocalization was stabilizing. Why? Because the electron gets to slow down and have lower kinetic energy. Okay? We haven't talked about the potential energy of the electron yet, and we will, but this is the reason why electron delocalization is stabilizing. One other point that your text makes is, and this isn't going to be a wave function that's representative of anything real. Let's do sort of particle in the box and think about a standing wave versus, we'll put the zero line here, and overall, on average, which of these two functions has the higher second derivative? Option A or option B? B, higher second derivative. And that means it has higher kinetic energy, and therefore it is the less stable of these two standing waves or wave functions. Now, if you took 351 from me, we talked a lot at the beginning about how the more nodes an orbital has, the more time the wave function goes through zero, the more energetic it is. And this, for example, here we go through zero is a node. This conclusion that the more number of nodes an orbital has, or a wave function has, the more times it goes through zero, the higher energy it must be, comes directly from the second derivative kinetic energy operator. Here we've got two nodes. And again, overall, as you look at this wave function, where is the slope changing more rapidly for B or for C? It's changing more rapidly for C. So in general, the more nodes an orbital has, the higher in energy it's going to be, because going through zero all those times requires massive changes in slope and therefore higher kinetic energy. All right, questions? And please don't feel embarrassed to ask questions that you think are things you should already know, because likely if you don't know it, I don't know it, and we'll learn together, okay? All right. So now let's go to the most famousest of chemistry equations, maybe not the most famousest, I don't know. the Schrodinger equation, which tells us that if you apply the Hamiltonian operator, which we're just representing with h, this is some function, some math that we can apply to the wave function, it will return an energy value times that wave function. And the Hamiltonian operator contains two sort of components. It contains the kinetic energy operator and then a potential energy operator. The kinetic energy operator has this form for particle wave functions that are defined in XYZ coordinates. One thing we will not deal with at all is the fact that as soon as you get to hydrogen, they drop XYZ coordinates and go to polar coordinates where there's an R and two different angles, a theta and a phi, and I don't know how to do calculus in polar coordinates, so I'm sorry, but we will just ignore that. The potential energy operator depends on the situation that you're in. So if your particle is a spring, you might have a potential energy function there for a spring based on whatever the law is. In our case, though, we're talking about electrons around a nucleus. So that potential energy operator is basically going to be Coulomb's law, which you learned about in physics, which tells you basically opposite charges attract, and the closer they are together, the more attractive the force. Okay? So let me show you what your text shows you for the general form of the Hamiltonian. This is going to be important because we're going to refer back to this when we start talking about computational methods. We're going to write it all out, and then we're going to automatically ignore 2 or 3 parts of it. But it's important when you're learning something to understand the simplifications or the assumptions that you're making. All right, so let's imagine a molecule, and the molecule has n, where n equals the total number of nuclei, except I can't spell or write when I'm talking. Total number of nuclei. So this would be all the carbons, the hydrogens, the nitrogens, the oxygens, etc. N is going to equal, lowercase n, sorry, is going to equal the total number of electrons. Little m is going to be the mass of an electron. E will be the charge of an electron, which is actually the same but opposite of the charge of a proton. Let's see, m with the A subscript is going to be the mass of nucleus A. And so we're going to have MA, we're going to have mass of nucleus B, all the way out to however many nuclei that we have. Z is going to be the charge of nucleus A, and we're going to have charge of nucleus A, charge of nucleus B, on through all of the nuclei we have. With me so far? So we're just giving numbers and designations to each electron and each nucleus. We know their masses, we know their charge. R with the subscript A, and then I is going to be the distance between nucleus A and electron I. So we're going to have a ton of these R terms. We're going to have one for the distance between nucleus A and electron A. We're going to have one for the distance between nucleus A and electron B, and so on for all of the electrons. I'm getting distracted, and so on for all the electrons and all the, what in the heck is going on here? I don't even know, between all of the nuclei and all of the electrons. Sort of makes sense? All of those distances. Then we're also going to need the distance between nucleus A and B. And so we're going to have a bunch of those, R, A, B, R, A, C, and so on, R, B, C, and so on. Okay, and then finally, we're going to have our operators. The del squared A is going to be the second derivative with respect to x, then y, then z for nucleus A. And we're going to have tons of those for each nucleus. And then the del squared for I is going to be the second derivative of the wave function for nucleus I. Okay? And remember, likely by the time we get to hydrogen, we're taking that second derivative in polar coordinates. So just don't worry about the fact that there's an x there. Yeah?
Sorry, so you said nucleus I.
I'm sorry, electron I. Thank you, Kim. That's exactly right. Okay? So that's all of the things we had to write down. Now we're just going to put together all of the forces and kinetic energy that we should know about based on our understanding of the charge and the mass of these particles. Easy, right? Just only a couple of things going on here. There's kinetic energy, and then there's Coulomb's law, and that's it. Well, so our overall Hamiltonian operator some people put a hat on it and say that the little hat means something. By hat, I'm thinking about that carrot. That doesn't look like a hat. If you want to make a hat, draw a hat. But that looks sort of like a half rest. Baseball cap, maybe. So there's going to be a few terms in this Hamiltonian operator. The first is going to be this, minus h bar squared divided by 2. And then we're going to have here the second derivative for nucleus A with respect to position divided by the mass of nucleus A. And we're going to have n different kinetic energy terms for the n different nuclei. All we've done is we've brought these constants out front. So we're going to have this del sub A is going to operate on the wave function for nucleus A, and so on. Okay? So that's kinetic energy of the nuclei. Then we're going to have second kinetic energy for the electrons, and each electron has the same mass, so we can bring the mass of the electron out in front of our sum. We're going to calculate this for each electron from electron little a to electron little n, and the operator for kinetic energy here will be the second derivative of the position, or the second derivative of the wave function for electron I with respect to position. So this is the K kinetic energy of each electron. Okay, then we're going to have nuclear repulsion. And this is just going to be an expression of Coulomb's law. So, and there's some constants here which your text doesn't show. I looked them up, but then I'm worried I got them wrong. Coulomb's law is usually has these constants 4 times pi times the, and this epsilon is the permittivity of a vacuum. That's how much a vacuum can respond to an electric field, which isn't that much. And then we're going to take the sum of the following expressions. Charge of nucleus A times charge of nucleus B times, well, and actually, sorry, number of protons in nucleus A, number of protons in nucleus B times the fundamental charge increment of an electron or a proton. And then we'll divide by the distance between the distance between nucleus A and B. And we're going to do this for all combinations of the nuclei that we have. Only we don't want to count it twice, so maybe we're going to say we're not going to let A equal B. Okay? So if you remember Coulomb's law, actually, the one I remembered is that the force between two charges is proportional to r squared. So why don't we have r squared in the denominator? Well, it turns out that energy is a force exerted over a distance. So when you multiply a force by a distance, one of those r's goes away, and so what you have is a single r in the denominator. And that's the potential energy of having two nuclei that have like charges, but they're close to each other, versus being at infinity when it would be 0. All right? Okay, so there's more. Now let's do potential energy for nucleus / electron attraction. And this is going to have the same basic form, only it's going to be negative. It's going to be favorable because the charges are opposite. So we're going to do this for each nucleus from A to N and from each electron from I to N or whatever. This will be charge on the nucleus times charge of the electron squared divided by the distance between the nucleus and the electron. And again, this is Coulombic attraction between a negatively charged nucleus and a negatively charged electron and a positively charged nucleus. And again, if it were infinity, of course, the potential energy would be 0, and it's negative potential energy from there. Go ahead.
Why is the electron squared?
So Coulomb's law has maybe you remember K is the constant times Q1 is the charge on particle 1, Q2 is the charge on particle 2, and then the radius between 1 and 2. It's making it more complicated than it needs to be. Z is just the number of protons in the nucleus, and then E is the fundamental unit charge. So Q1 for the nucleus is ZE, and then Q2 for the single electron is just E. Does that make sense? Okay. Others? And then, and this is, well, all of it is, oh, sorry. Oh, yeah, Austin, can we hear you? Go ahead and unmute yourself. Why aren't you coming through? Internal speakers, volume up. Okay, somehow the audio for you isn't coming through on our end. Is there, I think there's a chat function that should be enabled. Let's see if you can type it. Oh, that's why we can't hear you. Just a second. Tripping. Audio control. Okay, try now. No? Oh my gosh. I will figure out how to do this. How do I stop sharing my screen for just a minute? Where, somebody who knows this, tell me how to do the chat. Oh, okay. Thanks, Austin. I see it now. The book doesn't include the 1 over 4 pi times whatever that letter is, epsilon. Do you know why that is? Yes. Good question, and thank you. I also need to start sharing my screen again. Okay. And we need to now hide this. Hide floating meeting controls. Yeah, the book doesn't show these constants. It tells to, for simplicity's sake, it doesn't want you to worry about them. I just felt it was sort of incomplete, and I wanted them there because it bothered me. So often in chapter 14, your book will say, there are constants here, which we're just going to assume that they're there, and that will be as it is. Is that okay? All right, thank you. And we'll figure out the sound issue remotely. It's probably something I've set funny on my computer. And then lastly, we've got, and this is something that I often forget when I'm thinking about atoms and molecules, you've got repulsion between two electrons. Okay, so this will be the charge of electron 1 times the charge of electron 2 divided by the distance between them. We're just going to call those I and J. And we're going to sum this over all possible combinations of two electrons in our molecule, but we won't count it twice. And this is electron-electron repulsion. Okay, so 5 different terms for the Hamiltonian, where actually each one of them is multiple terms depending on how many nuclei and electrons you have. You can see how this gets crazy complicated, and you can actually have I sort of have a feeling of appreciation for the people that did this math by hand in the 1930s and 1940s and were able to give us the picture of the hydrogen atom, which you can solve the wave functions exactly if you use this Hamiltonian. I don't know how to do it, and I'm glad I don't have to do it. But yeah, go ahead.
Yeah, that's the hydrogen atom is the only one that shows how to solve in general chemistry classes.
Right.
And last year when I first did that, the book had
Okay, so your PChem text had 10 pages of work showing how you solve it. Yeah, you can just Google it, and there will be things that try to take you through it. But I looked at it, and it requires you to recognize certain terms as actually being equal to some series with certain numbers, and that's where the quantum numbers come from. And I really got nothing there. I tried, I really did, but I got nothing.
when we did that,
It didn't have repulsion terms. Right, because in the hydrogen nucleus, it's just 1 proton, 1 electron. So that gets rid of terms 3 and 5, which would simplify things dramatically. Okay, but I just want you to have a feel for what that Hamiltonian contains. Frankly, when I saw the Schrodinger equation, and oh, it's such a simple equation, there's 2 things there. What the heck does the H mean? The H means all of this. What the H is what you can now say when you look at all of those terms in the Hamiltonian. If you don't like mild swear jokes, you can write me a note and I will attenuate them. I'm sorry. Okay, so we're gonna go ahead. Kim, did you have a question?
Oh, no, sorry.
Okay, you were stretching. That's okay. I like to stretch. This gets a little too complicated. And so one of the things we're going to do is to make the famous Born-Oppenheimer approximation, which is basically this, that electrons move much faster than nuclei. And if nuclei move, the electrons can rearrange themselves almost instantaneously. due to changes in nuclear position. So we're going to imagine that the nuclei are motionless, which of course they're not in reality. And then we're going to consider only electron motion. What this is going to do for us is this allows us to get rid of, and I will highlight in, I suppose, we gotta choose for colorblind. So we'll highlight in pink maybe the terms that, no, actually we'll just put a pink X through terms we can ignore now because of the Born-Oppenheimer approximation. So nuclear kinetic energy goes away. And then it turns out that nuclear repulsion is going to go away. It's real. It doesn't go to zero, but it's constant. And so we can ignore it. I don't really have a greater justification for it than that. I don't know whether that means you just... Well, actually, if you're going to assume the electrons don't move, the nuclei don't move, then you can actually calculate term 3 very easily, probably just for the spreadsheet. So you don't need to involve that in all of the crazy math that we're going to do. So the remaining terms are the ones that we're going to focus on. And so this is our kinetic energy of each electron. This is the nuclear electron attraction. And fortunately, we only have to worry about the electron moving relative to each nucleus, not the nuclei moving. And then electron-electron repulsion. So if you want a way to remember how the Born-Oppenheimer approximation, aside from what I've told you, I suppose those letters B and O are like the first two letters of the Book of Mormon, and in the Book of Helaman we just read Mormon's statement that surely it is the earth that moveth and not the sun, so surely it is the electron that moveth and not the nucleus. That's a thank you, Kim. That was a stretch. That was a stretch. Okay. All right. So that's our simplified Hamiltonian. And as I told you, what we're going to do is we're going to try to find wave functions that are solutions to that Hamiltonian. You've got to find something here that when you apply the Hamiltonian to it gives you energy as an eigenvalue and spits back out the wave function. And if we can identify what that wave function is, then we can calculate anything that's possible to know about that particle. So what do? Well, you can go look up how to solve the wave function for the hydrogen atom. But we're not necessarily interested in that anymore. What we want to know is, what about a molecule where you've got two things interacting together? So what we're going to talk about now is something that's called the two orbital mixing problem. That is, I'm going to bring two atoms together, and let's just imagine they're hydrogen atoms. And I want to mix them together to generate two new molecular orbitals. This is how another way of putting this is, how do we formulate our guesses for what the wave function should be for a molecule? And the answer is, we do something that's called linear combination of atomic orbitals. I won't try to write all of that down. What this means is we're going to make molecular orbitals from a basis set of atomic orbitals. The basis set of atomic orbitals is the alphabet of orbitals you have on each atom that you're bringing together that you're going to combine to make the new molecular orbitals. So let's just imagine we've got atom A, and we won't even say what atom A is, and atom B, and they each have an electron, and we want to combine atom A and B together to make a molecule. And let's just keep it simple now. Let's just have one orbital on. So this Greek letter phi with the subscript A is going to represent the wave function of the electron on atom A. And then phi with the subscript B is going to be the wave function of the electron on atom B. So if we bring A and B together to form a new molecule, what we're going to say is that we are going to generate the wave function. Our initial guess for the wave function is going to be one where we add the atomic orbital from atom A to the atomic orbital for atom B. And we're not just going to add them together. There's going to be a coefficient that's going to tell us how much of the atomic orbital for atom A contributes versus how much the atomic orbital for atom B contributes. Okay? With me so far? This is, if you took 351 for me and thought about this, this is like taking the 1s orbital on hydrogen A and adding it to the 1s orbital on hydrogen B and doing it in all possible phase combinations. Okay? But we want to be a bit more specific because we want to know now, mathematically, how much of this new molecular orbital is on atom A versus on atom B. And we're going to get that from these coefficients. To do this, what we actually need to do is we need to find values for these coefficients that minimize the overall energy of the molecule. We're going to begin with the hypothesis that the lowest possible energy wave function is the right one. And so what we're going to do is we're going to minimize the energy associated with this wave function. We're going to vary these coefficients until we get the lowest possible energy. So let's start with the Schrodinger equation. If we want to know the expectation value for energy for a particular molecule, what we need to do is take the complex conjugate of the wave function, multiply it by the Hamiltonian applied to the wave function, integrate that over all space. We're going to use a generic spatial term tau just to represent either polar or XYZ coordinates. And then we're going to do the same thing for energy, wave function, complex conjugate times energy times the wave function integrated over all space. Energy is a constant though, so we're going to be able to bring it out there. And I'm going to introduce a change in notation for simplicity's sake. People get tired of writing integrals from 0 to infinity and with d tau. So actually we're going to use bracket notation and we're going to drop the star too. Everything on the left side of the operator here, you're interpreting that as a complex conjugate of the wave function, but we're going to forget about that completely now because the computers are going to take care of it for us. This is the Hamiltonian operator applied to this wave function. And the bracket represents integrated over all space. Okay. And then over here, we've got energy times the integral over all space of the complex conjugate of the wave function times the wave function, again, integrated over all space. And you can treat these integrals as algebraic quantities. So if we want to know what the energy is, this is where I love the iPad because I can copy and paste. And you can't unless you're using an iPad. Those terms cancel out. And so what we have instead is energy equals the Hamiltonian integral divided by this integral on the bottom. Okay? So that's how we're going to know the energy. And then what we're going to do, and remember we defined the wave function up here. I'm going to copy that and bring that down. This is expressing the wave function as a linear combination of two different atomic orbitals. What we're going to do is plug that wave function in here to get an expression for energy that depends on those coefficients. And then we're going to find the lowest possible energy. We're going to find the coefficient that gives us the lowest possible energy. Okay? So how do we do that substitution? Well, we could just bring in that linear combination representation of the wave function. We apply the Hamiltonian to it here. And then on the bottom, we would have this expression, which is the same thing as saying the complex conjugate of the wave function multiplied by the wave function integrated over all space. Now, at this point, we can sort of forget that we're dealing with integrals and just do algebra. Yeah, Michael. Yeah. Yes, and the complex conjugate will be reflected in those actual wave functions. But you're right, we're sort of forgetting about that now. And it won't, I think, all taking the complex conjugate will do is get rid of the imaginary parts so that what we're dealing with is real. But yeah, we're not worrying about that in the math that follows. So what we're going to see is that because these are integrals, you can separate out individual terms and add them together. So we're going to take the Hamiltonian and apply it to this term, and then multiply this term times that. So here is the Hamiltonian applied to Ca times phi a, and then we're going to take Ca times phi a and multiply it through. Okay, and that's one term. And we're going to do that for each of these terms, right? So here's the yellow. Let's now use purple. We're going to apply the Hamiltonian to Cb and then multiply Ca. So that's going to give us Hamiltonian applied to Cb, phi b, Ca, phi a. And that's our purple term. With me so far? We're basically doing FOIL. We're multiplying two binomials. I don't remember what the algebra is called. And if you're a little bit confused at this point, that's okay. It's actually best at this point for you to just worry about doing the algebra, and then once we finish it, we'll take a step back and ask what does it physically mean. Okay, and we're sort of running out of time. So any last questions, and then we'll pick up with this next time? No? Okay. My office hours are 10 a.m. Monday through Friday. So feel free to stop by. If that doesn't work, we can meet other times by Zoom. And thanks, and have a good rest of your day. See you, Austin. Hope you are doing great wherever you are.